Hi, my name is Ken Rasmussen. I wrote the Microbiome prescription website, and today I want to talk about fuzziness with the microbiome. My background is actually in probability and statistics, undergrad and master's, and accepted for a PhD and did a bunch of PhD courses, but industry tempted me away, including industries like Microsoft and Amazon. And for a variety of reasons, I ended up becoming interested in the microbiome. I was a high school teacher. I even taught a variety of science college courses. So getting into the microbiome was not a big stretch for me. It was, okay, let's just take it in, having the scientific process well established. As I got into dealing with the microbiome and reading the literature and reading a lot of literature, I started seeing things which I said, oh, why don't anybody ever talk about this? Or, but, because there's sort of overtones which were never spoken of. And this little short video is talking about a bunch of these overtones. And now, these overtones do not scare me because, fortunately, working in probability statistics, operations research, having done that professionally for 30, 40, 50 years, literally 50 years for some stuff, and being in software, doing a lot of work in software, I know how to go about handling it. It is a different process. It is having to use mathematics heavily and probability heavily in order to make sense of the things and to reduce the odds of randomness, literally killing the results. So we're going to talk about fuzziness with the microbiome, and the image in front of you in some ways represented. Oh, a plant is something which is green. Yes, but you see 4 different types of plants there, all slightly different. Some will prick you, some will do other things to you. So let's go on. Okay, I often use the expression and advocate that you need a fuzzy logic expert system to work with the microbiome. No large language models, they just don't do it. They basically hide the hardcore reality. The fun of using a fuzzy logic expert system is, step 1 is we assume and we know that nothing is definitively correct. Absolutely no statement is correct. Each statement has a probability of being correct or a probability of applying X percentage of the time, but never 100%, never. And that means your whole system has to be built not on A causes B causes C, but A may cause B, which may cause C, but C may only happen if item D happens, and then things change, and you start getting into a hornet's nest, or a great entanglement, a Gordian knot, to use some classic analogy. The reason is very simple. Studies will give different results based on the age and gender. I often have read studies where, okay, this shift is seeing for diabetes for women, and this different shift is seeing for diabetes with men. Okay, same condition, but based on gender, 2 different things. Or things like obesity. These bacteria are shifted for somebody in the 20 to 30-year-old range, and these are different shifts for somebody in the 60 to 70-year-old range. So there's a ton of factors which will cause all the data you're working with to be different depending on the context, which of course means, okay, well, I want precise context to be absolutely correct. But the problem is we have sparse data. We don't have a ton of data. So first thing is, I see these 3 people laughing their heads off. There are no standards for microbiome. There are no such things. People say we should have it, but we don't have it, and that's a real nightmare, very much a nightmare. And what is the impact of having no standards? Well, Scott Jackson over at the National Institute of Standards and Technology, the people who should know about standards, says 97 different ways look at the same raw data, not the same sample, but the actual raw data. That is the data that comes out of a sequencer, and they will be interpreted differently. Okay, came across that, and I came across that after I took when Ubiome went out of business, I had samples there. I had their FASTQ file, their data files of my sample. Okay, I went and uploaded to Thrive Insight, which is now Ombre, Biome Site, and Sequential Biotech, which for a while there was offering free processing. And I said, okay, how many bacteria do we have? Wait a minute. One says I had 253 bacteria were identified. Another one says 632. And when I look at something like the amount of bifidobacterium, numbers were all over the place. So in other words, what is the result? We have absolutely no definitiveness. Keyword is definitiveness. We have fuzziness, and that is the term we want to use, fuzziness about what we actually do have. If you want to do some more reading about it, there is a Taxonomy Nightmare Before Christmas, and there's a link to it, which I describe more and more the thing. When that came up, I sort of said, okay, guess what? That means that little fact that we have no standards impacts everything from one end of the microbiome to the other end without mercy. Without mercy. Now, you can pretend you don't see it and just say, okay, I'm Blinker. What my lab test says as a result is the truth. Okay, welcome to the world of religious microbiome analysis. Some people will go that way. Me, I rather make use of my background, probability, statistics, operations, research, and accept the lack of definitiveness upfront and strongly, and get on with doing whatever we are able to do. And there. So let's go on. First thing is, what's a study report may not be duplicated. Study find, oh, we have these bacteria shifts are strongly associated with Parkinson's, with Alzheimer's, with diabetes, with mast cell activation syndrome. Guess what? The result comes out, you get your study, you try and replicate it, and because you use a different lab or different sequencer or a different pipeline, you don't get the same result. In fact, to make it fun even more, you get hold of the raw data from the clinical study and you push it through your favorite pipeline, and you get totally different results. Now, that presents some lovely challenges. And unless the glorious President Trump mandates a particular pipeline to be required by law, we are stuck with it because there are too many advocates for their own. We have a still better way of doing it who will keep doing it, and the problem is the older studies use different pipelines, different processing, which means the old data is not particularly valid anymore, or is it? So basically, we have, first of all, what study report may not be duplicated. We have question marks there. Question marks that usually are not spoken about. And basically, we have a problem of comparing apples to watermelons. Both are round. What more do you need? So, one of the solutions I've worked on and derived is my website, Microbiome Prescription, basically asks users to provide metadata about themselves. Do I have diabetes? Do I have Alzheimer's? Am I a 15-year-old? Am I a 65-year-old? And then we do regression against the metadata for other people from the same lab, the same pipeline. And what we have found is that somebody uploads a new sample and give my symptom forecast, and generally it's been pretty accurate. I have got an email saying it's been shockingly accurate, as in hit. The top 10 symptoms predicted are the top or the 10 he has. So it works. I mean, and it should work because you are basically consistent from the sample to the particular mechanism to the results. It's all consistent. Bottom line is we can identify bacteria as reported by a specific lab that are likely cause and contributing to symptom, provided we get the sample database. Enough of them are the right size and the right things, and enough samples with specific metadata for specific conditions. which is now a data collection problem. Microbiome description basically does a carrot approach, offers people all sorts of suggestions and for how to better the microbiome, and as a result, they are willing to contribute metadata to help make those suggestions better. So that is workaround. If you're doing a pure clinical study, then your problem is getting a reference set, getting enough samples. You get a whole bunch of dilemma, and once you get your beautiful study and your report and you publish it, it's not highly usable in a clinical setting, because guess what? They may not be using the same clinical pipeline or the same sequencer. So it becomes trying to put a metric screw on an imperial bolt. Doesn't quite work. Sometimes you can get something with a bit of forcing. Other times it just won't, the threads won't connect at all. Now, when we go over to the modifier one, we have the same problem. The studies were done seeing how this particular modifier modified a microbiome. And sometimes we find a ton of studies which all report the same thing, in which case we give it a higher probability of causing an increase. We don't guarantee it will causing it. We're simply saying it has a higher probability. And then other times the studies will contradict each other, and we should give things a lower or reduced probability rate. Notice I'm using the word probability and weight because that is what the key of fuzzy logic is, using probability and weight. It's not doing a simple, naive, logical, oh, this increases that, that increases that, that increases that, and we're done. No, it is having to do a lot of calculations in the background or in the algorithm to factor in all these things. Let's take a look at a simple one. Here is from a site, and it's very simple. If you take a look at barley, you find 27 studies shows that increases lactobacillus. That's beautiful. You have a high degree of confidence. And in this case, if you check, you find there are no studies that says it decreases it. So you are happy. You have great confidence. Then you have Bifidobacterium 19, etc. Akkermansia is 9. So you have a whole bunch of things. And in some cases they're contradictory, some cases they're not. But in general, results are more consistent with modifiers and bacteria. But the main problem is generally the taxonomy level being reported on from most of these studies are at the genus level, not specific species, and sometimes the species is where the rub in the whole process happens. So it's not ideal, but we can at least get consistency, and if we don't get consistency, we go to adjusted probabilities. Now, when we go to condition studies, we have the same issue, and in some cases it is nice and easy. For example, I grabbed from my site data for obesity, and you see we have a whole ton of studies showing that obesity has a lower amount of Akkermansia municipa, but one study disagreed. That study could be because of the medical condition being examined or some other preconditions which cause different results. So we don't have as much definitiveness. We have something like, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have perhaps 1 opposed and what? Let's say 10 in favor. So we give it a probability of 0.93 causing a indicating that obesity is likely to be happening for this person. We go to different bacteria, Prevotella, and we find that it is found in studies to be statistically significant. But here we have a problem. We have more studies, we have the same number of studies saying it's higher and the same number of studies saying it's lower. Which is it? That's interesting. We know it was found to be statistically significant, but which direction is unclear. Then we go and take a look at something like Bifidobacterium, where we have this sort of disagreement, but when you find the rare studies looking at the species, you see that certain species are associated with higher and certain species with lower, and that suddenly makes sense. That the reason we have the Bifidobacterium going one way or the other depends on the distribution of the particular Bifidobacterium species. So now we understand the issues better, and the Bifidobacterium species are the key thing, assuming your lab test report at the species level, which is not always the case with 6 or even if it is, claims it is, we know that it is relatively low reliability, as in it may not be correctly identified. Okay, so now how do we deal with this latter case? We actually end up using percentile multiple times as a proxy filter. First thing is we don't know what is correct. We don't know if it's high or low, for example, Privitella. So what we do is over the entire population of samples, we set a high or low threshold for being too high or too low. Could be 5 percentile, could be 15 percentile. There's lots of magic goes on inside of those thresholds. So we don't know, but we set a arbitrary or semi-arbitrary threshold, and now we see how many times each sample matches that. That is, if it says Privitella is high and it's over the threshold, we give it a 1. If it says Privitella is low and below the threshold, we'll give it a 1. So we won't ever double count Privitella because it's ever high or low. You can't have it being both at the same time. But we do give it a notional point if it's in the high group or in the low group, and do the same with Bifidobacterium, notional in the high and notional in the low. And now, so we get a count of how many of the bacteria matching happens for this particular lab. And remember, labs won't report all the bacteria, only some of them. So we see how many matches we have, and we count out how many matches we have. So we have our entire sample set, and we have how many people have 0 matches, 1 matches, 5 matches, 15, 40, 25, etc. And now we go and take the count and convert them to percentile. In other words, let's say we have some people with 40th percentile, but 40th, we'll count of 40, and we find that only that 90. It's at 98th percentile. Only 2% has more than 40 matches. So that is 98th percentile. Okay. Then we set a threshold which we deem it to be significant based on the observed incidence of the, for example, obesity is 40% of the population or more, or 90%, depending on if you're in the US or someplace else in the world. Or, for example, Denmark and the US have very, very different obesity rates. And you basically set based on the incidence of the thing. For example, if the person has over 60th percentile, you say he's probably obese as your forecast. Again, all this process is lab specific. You cannot mix and match results from different labs. The results have been generally acceptable in regression testing, as in we have over 72% are correctly identified according to the metadata which was donated on the same sample. In other words, the methodology gives reasonably good results. Now, this methodology is particularly useful for rare conditions. Above, for the validation for the symptom, it works for common condition. If you're dealing with a rare condition where you don't have many samples with marking the metadata, then this approach will probably give acceptable results. So let's go on to the next part of our journey in the line of probability. And that is basically data is both valid when the same pipeline. Different pipeline basically puts fuzz, a cloud, a dark black cloud sitting over your results. If you're trying to apply it clinically, that cloud may be there unless you get cooperation from the lab to get the numbers and the data and the normal thing. Generally, we want to have a reference set of 100 samples from healthy people in order to be able to get accurate percentiles for each bacteria, which is the key. And ideally, the reference set, we would have metadata on gender, age, etc., so that we can actually have age-specific or gender-specific percentile ranking. Be nice to have more than 1,000, but 1,000 seems to be what is usually available out there for most labs, most of the good labs. Smaller labs, they won't have it anywhere near that number. It costs money to get the reference set, and that it sells the lab services, you're not going to get a reference set. We should have at least 30 people with a specific condition, ideally 300. These are not the happy people. These are people you're working with. And now with those people and the reference set, you can go and do statistical significance of what to look for, which one are the key bacteria. One of the challenges is we have overlapping conditions. We may have somebody who's obese with diabetes, with irritable bowel syndrome, has asthma, has a mast cell activation syndrome, 5 different conditions. So the problem comes separating. That can be done, but it does require some careful, non-parametric statistical processes. Not parametric, but non-parametric process to do it. So there's an opening soon to be able to do much better analysis, but you need cooperation from the lab. You need to get the data in. You may have to do your own in-house statistician who understands the issues, and taking them through this video may get them up to speed. And then you have the ability to do some good, solid, helpful things. Remember, the key thing is modifiers changing bacteria seems to be pretty stable, which is the sweet thing. Identifying the bacteria involved or that you want to change is where the challenge actually comes. So that's basically it. If you want to contact me, just contact me here at Research and Microbiome Prescription. My website, which is loaded with data, is a open science site, so you can get a lot of data for free there, and including references to studies being used. So it's just generally pretty rich. If you're interested, citizenscience.microbiomeprescription.com gives you the data sets which we are actually making use of, including data set with metadata, as well as an example of a cross-validated report on depression. So citizenscience.microbiomeprescription.com is well worth a browse. Okay, with that, I'll shut up and tell you to have fun.